welcome to another exciting adventure in the Data Club universe. My name is Roger. This is what I look like. Nice to see you all. Today we are going to be talking about the somewhat cryptically named topic, Xarray's children. What we meant by that is we're going to be discussing a library that in scientific Python at least is gaining a lot of traction, Xarray, and I'll explain what Xarray is and why you should care about it, but then also starting to look at how the downstream impacts of Xarray and some other libraries that build off of Xarray. So the first thing to do for folks who haven't been here before is go to github.com/Columbia Data Club, and from there you'll find this screen. Then go to Meetings and click on 2023, and you should see April 13th Xarray's children.ipynb. And from there, click on that, and you then will come to a page that has a notebook with a Open in Colab icon. And when you click on Open in Colab, it will open in Colab. Thumbs up, thumbs down. How are we doing?
Something wrong with my Wi-Fi?
Oh, the Wi-Fi. A perennial challenge.
Where is the Open in Colab?
So go back
Oh, back.
and click just once on the folder. And then click on where it says April 13th. Yep, click there just once. And then click on Open in Colab.
Oh.
Nice. Oh, great. Wi-Fi still troublesome?
You were restarting, so it'll take
Oh, it
a
was.
5x.
Hey! All right. So, Xarray's children. I'll make this a little bit bigger. And so the things we're going to do today, talk a little bit about Xarray as a tool for data analysis, then introduce a couple libraries that build off of Xarray. Because I'm a geoscientist, these are going to be geoscience-based libraries. But one of the points, I think, of this hour and a half is to say that a powerful tool can be used for many different purposes. So the features that made it necessary for people to put a lot of energy and continue to put a lot of energy into Xarray as a tool, I think could make it useful for a number of applications. In the Python universe, the library that you often come across for data analysis, especially in industry, is pandas. And pandas is this library for mostly two-dimensional data and two-dimensional tabular or labeled data, right? So Xarray is the answer to what happens when you have more than two dimensions. And the problem that you run into if you work with just bare metal multi-dimensional arrays is that you have to keep track of whether the temperature index is the first index or the second or the third, and it quickly becomes pretty hard to not introduce bugs into your code because you're trying to keep track of this pretty opaque metadata. So the solution that folks have come up with in geoscience is Xarray. And the way Xarray is organized is with a set of nested data structures, as shown in this graphic here. So you have individual variables, such as temperature, such as precipitation, such as latitude, longitude, and those variables have coordinates and dimensions, which are then wrapped up in data structures that are data arrays or groups of variables data sets. And so typically we're going to be talking about data arrays and data sets, which are these data structures that hold variables and their coordinates. Underlying Xarray is the low-level NumPy array that forms a lot of the foundations of computing in Python. And the value of having NumPy underlying everything is that it's very fast because it just wraps C and C++ based code. So we have a data array, and it's a structure that has dimension names for axes and coordinates, and then it also can hold a bunch of metadata attributes. Yes?
I'm sure I asked this last time, but coordinates are not just latitude and longitude. Coordinates are effectively the different indices that that you have.
Good. So dimensions are the indices. So let's see. Here's a good example. If you're in a geographic reference frame, it's often the case that so you're looking at the North Pole, and maps are often in X and Y, so like meters X and meters Y. So say you have data that's tracking sea ice through time. It's X, Y, and time. But you want to know the latitude and longitude of, you want to have latitude and longitude associated with your sea ice because the data analysis that you're doing is in latitude and longitude. Latitude and longitude, like reprojecting data from X, Y into latitude and longitude means that the coordinates, which are lat long, will be two-dimensional coordinates because each latitude or longitude point will have an X and a Y. So the dimensions are X, Y, time, but the coordinates then, you would have latitude and longitude as additional coordinates. So dimensions have to be one-dimensional, but coordinates can be multi-dimensional. Does that, as an example, help?
Can you give an example that doesn't actually use latitude and longitude?
Sure. Let's see. It might help if we find one.
Okay.
So that we have something to hold on to. But I think this is a crucial question that we should spend some time on. So the first library that we're going to look at that bases itself off of Xarray is called MetPy. And this is for meteorological data. And the reason I want to introduce MetPy is that it profits from another Python library that solves a pretty fundamental problem, which is units. So if you're multiplying dollars by hours, you just have a naive array that's dollars and a naive array that is hours. If you mistakenly have multiplied your hours by 60 and it's actually in minutes, but you haven't kept track of that, then you could mistakenly make the wrong calculation because you've mistaken your hours for minutes. And so the challenge then is, is there a way to do computations with a library that can keep track of different units, so that when you multiply, so that the hours column and the dollars column both have hours and dollars associated with them, so that if you divide the hours by 60, then you're multiplying minutes by dollars, and it keeps track of that. So MetPy does this, and also has some plotting features that I think are kind of cool. Okay, so MetPy is going to integrate Xarray and integrate this Python library Pint, which it does units. And so the first thing that we do whenever you're working with Python is we have to import a bunch of libraries. And it's going to tell you Google didn't author this, which is true, but do it anyway. And this first block is necessary because the libraries that we are running aren't natively installed on the Google Colab environment, so we have to use a package manager called pip. And there's a bunch of lines here of code because on the back end, the plotting library that MetPy uses, there's basically just some issues with versions, so this is a workaround that works. So once this runs, the next thing we do is import a bunch of libraries. So we are going to be using datetime, which is a built-in Python library that helps manage dates. We're using Xarray, and y'all are probably familiar with this, but the way we typically import libraries is with an abbreviation. So we, because nobody wants to type Xarray over and over again, we say import Xarray as XR. We're importing Cartopy, which is a mapping library, and then a bunch of different sub-libraries or a bunch of different functions from MetPy, and then NumPy, the baseline array library. And I think I've just successfully run that. Okay, great. So let's import stuff. And in past demos, we've spent some significant time cleaning data, because a lot of what you do in this data life of ours is finding data and realizing that it's not in the right format. And since this is my last presentation of the semester, I decided that I was going to use data that these libraries have built in, so it's already clean. So for once, we are not going to talk about cleaning data. I'm thrilled. Glad you're here with me for this. So let's open our beautifully clean data set. And this data set is going to have a bunch of different dimensions, and may not be the best data set to look at the difference between coordinates and dimensions, because in this case, every coordinate is associated with its own dimension. So in this case, there's not actually a need to distinguish between them. But what you notice here, if you're looking at Xarray for the first time, is that you have dimensions listed at the top, and then you have coordinates, and then data variables. So we have relative humidity, we have temperature. Isobaric means equal pressure. And each of these data variables has a bunch of different coordinates. So, has a bunch of different coordinates. It has time, it has isobaric, it has latitude, it has longitude. And open up some other portions of this, and you see that underneath, under the hood, the indices that it is using in its dimensions to keep track of the data are all pandas indices. So Xarray is using pandas to keep track of its data. I think eventually they're going to find a way to not use pandas anymore and just have a built-in indexing, but for now, that's what they're using. And this data set also has a bunch of attributes. So attributes are kind of floating. It's like you're walking around with a balloon. The attributes are kind of this balloon floating behind your data set, like that tell you stuff about the data but don't interact with any of the computation. I'll flag that let's put a pin in the not interacting with your computation because we'll come back to that. But yes, so this is coming from the National Weather Service. And a crucial point about Xarray is that each dimension has to have unique values. So if you imagined a book that had 3 pages that were labeled number 6, and you went to the index and it said, oh, go to page number 6 for the details about President Bollinger, and then you went to page 6 and then realized there were 3 different pages 6, it wouldn't work. So in the same way, Xarray requires that indices are unique, and it can cause problems if they're not. So let's start to dig in. So we noticed that there are a bunch of different data variables that each have these dimensions. So we defined data as this. We opened the data, xr.openDataset, and used that to get data. So now the Xarray data set is stored in this data variable. And so in this next cell, what we do is we say, let's use this bracket notation, which indicates in Python that we're going to select. So let's select one variable, temperature isobaric, and then Jupyter Lab and this online version, which is a little bit different, Google Colab, always print out the last thing that's in each line. So now we have temperature as a data array. Remember, data sets can contain multiple variables. Data arrays contain only one variable. Now we've got temperature as its own variable. Are there any questions before I keep plowing on? Good. Cool. Okay. Because from here on in, I'm going to start talking about things that are built on Xarray. Right. So we've got this. So metpy is going to take this Xarray data array in, and the one of the innovations of metpy is that in the climate and forecasting world, there are these climate forecasting conventions that lots of data sets have, and if the data set doesn't have them, you can manually add them. But basically, the point is, MetPy can identify coordinates of a number of different types, and one of them is time. So if we run temperature.metpy.time, then we get out this date time, this array with a bunch of date times that are stored in it, and you can access multiple coordinate systems at the same time. So if we have accessed x or y coordinates, we can look at that and see that we've extracted the, in this case, longitude. There are a bunch of different ways to select data in Python and in Xarray, and MetPy uses many of those. So the way that Xarray allows you to select data is through this .cell method. If you're familiar with pandas, pandas doesn't have this. Typically, if you want to select something in pandas, you have to say something like, if you have a data frame, you have to say df dot where df dot time is greater than 10, and that will give you like the subset of your data frame. That's not the case here. This Xarray is a little bit more discursive. So you can select based on dimension. You can select a certain time, and in this case, we're going to select access heights that are at a certain elevation at 1800 hours. So here's where it starts to get, I think, cool, because the problem that we identified was that if you don't have units in your data, then you can mix up what units you're talking about. I brought this up with my roommate last night, and he was like, "Oh yeah, I just did that. I was doing a problem set, and I used the wrong. I thought meters were kilometers, and it totally screwed everything up." So Xarray defaults to unit naive array types. So if we want with MetPy to preserve unit correctness, we have this quantify method, which is so named because in Pint the quantity is the sort of unit of discussion. And it would help if we ran all the cells in order, so make sure you run heights. Okay, so we run heights.metpy.quantify, and let's look at, actually let's go back here and look at heights before.
Can I ask a quick question?
Yeah.
I think I maybe missed this. Where does the Xarray data set get the MetPy member from?
Yes. So how is it the case that we could say heights.metpy?
Yeah.
So once you've imported, that's a good question that I'm going to give an answer to. But I think the technical answer is going to be under the hood. But when you import MetPy, it and Xarray at the same time.
MetPy hijacks Xarray like behind the scenes?
MetPy, maybe, I don't know about hijacks, but like MetPy, yeah, MetPy is kind of parasitic on Xarray.
Okay.
So it gives you the capability. Xarray now has this little thing attached that you can access if you need it.
Because with the progress bars last time, we had to run a separate function, like an initializer function, to add the progress bar methods to pandas,
Yes.
so that you could do progress apply or whatever it's called.
Yes.
But it looked like you didn't have to do that.
I did not have to do that.
Okay.
Yep. Okay, so naive Xarray, we have heights, we have this data array, it has latitude and longitude, and we have these values. And then, crucially, it has, does it have, it should have, GPM might be what we're looking at. Okay, but so we run heights.metpy.quantify, and what comes out is this Xarray data array that has a unit, meters. And that unit meters is going to stay associated with the array, the data array, even if we perform computations on it. So we take the zonal mean, like the mean over longitudes, and we then have a one-dimensional data array that still has units in meters. Xarray has built-in plotting capabilities, so we can quickly check it out and see that we're looking at latitude from low to high, and geopotential height goes up and then drops. And I'll show you why that is in a second. But the innovation here is that we now have meters. And that comes with some fallbacks or some consequences, such as the trade-offs that we in other lectures this year have looked at with Xarray and memory. So now is not the time to spend a ton of time talking about Dask, but if you ever have to deal with a lot of data, Xarray Xarray is for you, because it has under the hood strong connections to this lazy computing library called Dask that allows you to do basically, instead of you press go, you say one array plus another array, press go, and the computer starts working. Instead, if you are working with Xarray and Dask, you say one array plus the other array, press go, and what happens is the computer behind the scenes builds a graph, task graph, for what computation should happen, and then only when you finally say, no, actually compute, does the computer go, which means that you can work with larger data sets and break them into smaller pieces before performing actual computations. All of that to say that asking Xarray plus metpy to associate quantities with, or to associate units with data, if you're not careful, can trigger the computer to load everything into memory, which could be an issue. Right now, it's not possible to save units with arrays, so you can remove the units through this dequantify. Some other features that I think are useful include the ability to select with units attached. So here we're saying, let's look at what units.degrees north is. Not totally helpful, but you see that units.degrees north is pointing to a utility function within pint. So that's the unit library, and it's a unit that supports math operations. Okay. So we are selecting heights at 45 north and doing so with units. You also can convert units. So here we're saying, let's come back to our temperature, and we're selecting only the first time. So this bracket notation selects naively on time. This is a little bit probably less good coding than .cell because it's less descriptive. But for our purposes, it's fine. So then we are taking one time step and then tapping into metpy, the metpy Xarray accessor, and then saying, let's convert temperature into degrees C. And now we have temperature in degrees Celsius. But perhaps you actually want temperature in degrees Kelvin. So then you say convert to base units, and you have the same array, but in units Kelvin. So part of the power of Pint is that not only does it have a pretty large back-end built-in set of units, but you also can define your own units. So I was looking at I thought very, very strongly about spending even more time talking about Pint, and then realized that it's actually distinct from Xarray. So Xarray's children spending time talking about only Pint was not actually the right move, although there is an Xarray Pint library, but it's less well developed. But the point is, in the documentation of Pint, they show how you can define, if you don't want meters per second, you can define thirds of meter per second, like as its own unit, or like snail's pace, or whatever. So pretty darn powerful. And you can do the same sort of unit conversion for coordinates. You also, within metpy, can always reach in and select the underlying array. For all of Xarray's strengths, it is not as fast as pure NumPy. Anytime you're adding layers of something on top of pure code, it won't be as fast. Just like it's very hard for Python, even if it's wrapping C, to be as fast as pure C code. Just like pure C code is not as fast as machine code typically, but nobody can write in machine code, so of course people can write in machine code, but like Okay, and finally, it's possible to access the underlying units. So now let's look a little bit at ways to plot and ways to use this in data science. Any questions before I continue? No. Good. Okay. So we're going to import some libraries from declarative. So one of the things that folks in MetPy came across, and if you spend a lot of time in, I would say probably most coding libraries, you've also run across this, is that building there's a pretty big gulf between building a really simple plot and building like a figure quality plot or something that's good enough to sign your name off on, because there's a lot of customizable features. So Xarray, or so Xarray, MetPy have all, pandas too have all wrapped the underlying plotting baseline matplotlib, like the workhorse plotting library. They've all wrapped that with convenience plotting capability that makes it a lot easier to, with a few lines of code, make a functional plot. And right, so to look at this, we are going to open a different but similar data set. This is a time slice from 2010 of some atmospheric climate data. And once again, we have an Xarray data set that has a bunch of different dimensions. And actually, let's so one thing to notice is that we have this metpy.crs. CRS is a coordinate reference frame, and if you work at all with geographic data, you'll find that you start to bless any people who have created data that have this kind of metadata, because if they have it, then you have to add it manually. But the and the ecosystem for dealing with geographic data in Python is pretty diverse. MetPy has built some of that in, but good. Okay, so first we're going to select our time, create a variable, a date time variable that has the time that we want. And then we're going to, as we did before, select a subset of these data. And this is something new to talk about. Xarray has this slice notation. So in pandas, for instance, you might have to do something like, if you wanted, come on, live coding is never, never a good idea, but let's, for the sake of discussion, let's select let's select just a latitude, longitude. Oh dear. Going off script here. Well, in pseudocode, in pandas, if you wanted to select data between 70 and 10, you probably would have to do df where df.lat. You would need df.lat is greater than 10, and df.lat is less than 70, and that is how you would sort of slice out multiple, get a range. Xarray makes that easier with this slice notation. Okay, so now that we've got a data set, we are going to add a variable, wind speed, using this metpy module, npcalc, which we loaded earlier. And let's see how much information we can get on it. In this case, we're not given that much. But npcalc has an attribute .windspeed that is going to allow us to compute wind speed from x, y, u, v coordinates, east, west, north, south, and it's taking in pint quantities. So we're passing in the u component and the v component, and what we get out is wind speed. And so then typically you would have to write this big sort of mound of plotting code in order to turn this wind speed variable into a plot of some kind. metpy makes that a little bit easier with plotting syntax that instead of is one step higher up. So since meteorological data tends to ask for contour attributes, the metpy plotting syntax has abstracted that into a few different types: a contour plot, a filled contour plot, barb plot. We're going to look at contour plots and filled plots. And so here we go. We're going to say we loaded earlier. Contour plot was one of the things that we imported from metpy.plots.declarative. We imported contour plot. We also imported map panel container plot obs. And so we're going to instantiate a contour plot. Let's contour 2. So we have this metply.plots.contour plot. And then we're going to start adding things. We're going to add in data, but all the data. So that's going to have dimensions, like 7 different dimensions. But notice that time, height above ground, and height are all one-dimensional. So if you did squeeze should do it. You would get rid of the extra dimensions. You could squeeze them out. They would stay. So here's actually, comes back to your question between dimensions and coordinates. If you, in Xarray, want to reduce the dimensions of your data because you have dimensions that are only 1, .squeeze does that, but they stay as coordinates. So you can have coordinates that are not dimensions, just like with the latitude and longitude. Now we have this data is only indexed on 4 dimensions, but it has a lot more coordinates. And we could then, any coordinate that is not a dimension, you could say expand dims time, and then we would have time back as a dimension. If we don't have time as a dimension, I don't think we can say time equals, come on, oh my gosh. I don't think we can say time equals this, because we can't select based on coordinates. You can only select based on time, based on dimensions. But expand dims time so that we have a time dimension, and then we can select the 1. Okay. So we've added, so contour plot now is associated with the full-on data set. We say we only want the field that is geopotential height isobaric, and we want a certain level for the contours. And we've already defined what time we want to be plotting in, set the contours, set line color. These are things that you typically would have to specify within something like, you would have to do fit, and then subplot keyword, you would have to do projection keyword arg equals, subplot keyword arg equals projection equals, I'm going to not go down the rabbit hole of showing you exactly how you would make the plot that you're about to make without this, but you would need to be specifying every detail of this plot. And now we don't have to do that, which is amazing. Okay, so we've specified line style, etc. We're going to do the same thing with wind speed. So we did geopotential height as a contour plot. Now we're going to say, let's make a filled contour plot with wind speed at the same level, same time, set the contours, set the color map, place the color bar where we want it. And then finally, we are going to add the data to the map. So we've now instantiated this map panel. We're going to set the area of the panel, choose the projection of the panel. Is everyone familiar with what a projection is? No stress either way.
High school level projection.
Yeah, totally. So the challenge that cartographers have been dealing with since they figured out that Earth was round is that Earth is round, and you can't actually, there's no way to slice the skin of the Earth and put it on a flat surface without any distortion, there's always some sort of distortion. Like, think about if you have an orange peel and you peel it and you try to smush it flat, it'll rip apart in a bunch of different ways, but it will still be distorted. So there are tons of different ways that map makers have figured out to project the data from a sphere onto 2 dimensions in ways that don't distort the data in various ways. So you can have equal area in some places, but then the distance between points might not be the same as it is on the sphere. Or you could have equal distance, but then some continents look really tiny and some look really big. This is like the Mercator projection that you probably saw in high school makes Greenland look enormous, much bigger than it actually is, because the high latitudes are dramatically expanded, because what Mercator cared about was distances, because they were sailing in the Atlantic. Please jump in if I'm saying things that aren't right, because I know you've thought about this a lot.
It's not the distances, it's the angles.
Oh, perfect. Yes.
Yeah.
It's the angles. Yeah. So one can go to various degrees of map nerddom, which I think are delightful. But for our purposes, what's important is that whenever you have data that is geographic, it will need to, and you want to make a map of it, it needs to be projected into some reference frame. And just because I'm familiar with this, just to look at some of the different options. This is Cartopy, which is the Python plotting library. So the default is plat Xarray. However, Albers equal area, commonly used for maps of the coterminous United States, because it has equal area, but for the US, or for a certain area wherever you specify, but not equal angles. Other options: azimuthal equidistant Lambert conformal conic. So what we're going to be using is LCC, Lambert conformal conic. Here's Mercator. Look at how big Greenland is. It's enormous. Greenland is not that big, nor is Antarctica that big. Antarctica is smaller than the US, except in this projection. Let's see. Oh yeah, polar stereographic, or stereographic, is another one that's often used. Anyway, if you're ever curious about why maps look the way they do, now this is a little bit of a kernel of that to seed in your memory, so that you have a place to start. All this to say, we're going to set the projection of this map to Lambert conformal conic, and we want certain layers. This syntax is something that we'll pause on for a second. We've talked about this in previous weeks, but in Python, there's this concept of f strings. So if you want if you have a string, if you want to print, let's say GPA equals 4.0, and you want to print my GPA is 4.0, you could do my GPA is comma 4.0, but it's often cumbersome to do that. So instead, what Python allows you to do is to put an F in front and then put brackets, and it's like a little tunnel into the string, and then my GPA is GPA, and it's sort of inserted there. So, and pretty sure that you can put computations inside there, which is what we're doing kind of here. We're calling a certain level and a certain time. And you've got a
What?
oh, no, I thought you were you had a question. Okay. And okay, so then we've associated both cfill, which we defined as this filled contour plot, and contour. We've associated both of those as, defined those as plots in this panel that we've created. And then finally, we put the panel into a figure, define the size of the figure, and say, or we create a container for the panel and then put the panel in. Yes.
So panel.area, maybe you said this is latitudes and longitudes?
Correct.
Okay.
And let's look at that code. Well, we haven't defined it yet, so that will be helpful.
Sounds like the US.
You guessed it. Yes, but basically, yeah, we can define this attribute, and it goes x, y, so longitude, latitude.
And then once we have a plot, can you tell me where the data for panel layers is coming from?
Yes.
But I'll wait until you have a plot.
Let's run this. And delete that. And run this. And run that. And it's going to have to download. So here's the answer to your question.
Got it.
We so usually you would have to, so what this library is using under the hood is CartoPy. So you would have to from import cartopy.feature as cfeature, and then cfeature.natural landform or whatever, like natural earth. So we can click on this, oh dear. Actually, I think this is a data file, but basically there's a library that CartoPy interfaces with that has these different shape files.
So it's a shorthand for natural Earth's shape files.
Exactly. It's a shorthand for natural Earth shape
so like
files.
states is probably the admin 1 or whatever it is, or admin 2. Okay.
Yep, exactly. So, and what comes out is this, I would say, gorgeous plot. What you're looking at, by the way, is the Gulf Stream. So we are up at 300 HPA is 30,000 feet, give or take. And what we're seeing is the lines of equal pressure, the geopotential height. So higher where there is the jet stream, lower where it's not. I'm not an atmospheric scientist. So we would run pretty quickly into my knowledge limits on this. However, from a data science perspective, it's pretty darn powerful. Jetstream goes up to 200 miles an hour. Most places are at that height are more like 50 miles an hour. Cool. Okay, so we build this as Xarray's children, and one cannot talk about a single library and call it children. So we get a bonus round, which is the Open Global Glacier model, with a guest appearance from this smaller library called Salem. This may be a bit niche, but it is so cool. OGGM is a large enough library that it has a logo. Salem is not, so. But as with everything, we first have to install a bunch of boutique libraries. And the Open Global Glacier model is the first model that is extensible enough that scientists in the last maybe 3 to 4 years have finally been able to estimate the volume of all glaciers on Earth. There's over 200,000 glaciers. And until we had really good satellites, it was very hard to even figure out how many there were and where, because you need satellites covering the entire surface of the Earth at very regular intervals. Okay. So we're loading a bunch of different libraries in. Now we're loading in GeoPandas, which is one of the strong geographic Python libraries that interfaces with pandas, as you could imagine. Okay. So the reason to look at OGGM briefly is that OGGM also uses units like MetPy, but does so in a perhaps even sort of more built-in way. So this code is going to set up OGGM with a bunch of parameters, not worth going into really, but basically what we're going to do is pick a single glacier to look at. The glaciers that we're choosing from are from the comprehensive catalog of glaciers on Earth called the Randall Glacier Inventory. We're going to choose a small glacier from Alaska to look at. This takes maybe a minute. And here we first are going to once again load process data, and then start to do computations on it.
Is that base URL pointing to like a mirror?
This base URL is pointing to a.
Or is OGGM only in one place?
I think it's pointing to a mirror.
And I guess it's okay. You can keep on moving.
Undoubtedly, it's stored in multiple places. Randolph Glacial Inventory is published, so I think this is probably just a convenient long-term storage. If it's at University of Bremen, they're pretty stable. Yeah. Okay, great. So we're going to load our data, and we've got a bunch of data variables. Hopefully Xarray is starting to look a little bit familiar, the structure of it. And we are loading Salem, which, like MetPy, piggybacks on Xarray. And in this case, we've created a variable called smap that is basically going to house the metadata that we need to treat this geographically. Okay, so the data set that we're working with has both model output associated with it and observations associated with it. And what we're going to do is take the velocity data .its live and say we only want that velocity data where we have a ds.glacier mask. So let's look at that briefly. ds.glacier mask is this binary ones and zeros mask that is saying these are the outlines of our glacier. And our velocity is also a two-dimensional velocity map, but we have velocities everywhere. So we're saying we only want the velocities where we have the glacier. And Xarray has this convenient .where that says anywhere that there's anywhere that it's non-zero, keep the value, and anywhere that it's not, make it nan. There's also a more powerful xr.where, which we could do the same thing with if we did .mask. Anywhere that it is mask, put this. Anywhere else, mp.nan, and we should get. That's because it's not called mask. Glacier mask. Glacier mask. And we should get the same thing. Yeah, cool. But this is nice because you could then say not nan, but make it ones everywhere else. So it's a very powerful way of slicing out data and manipulating it. Okay, so we've got these different velocities, and now because we don't have the MetPy gorgeous built-in plotting, we got to do it by hand. But Salem is helpful in this respect. So we are using Salem to transform the x and y values onto this projection. We're saying the CRS, the coordinate reference frame, is the coordinate reference frame that we defined that is associated with the glacier variable, or with the glacier data set. And then we are plotting a quiver map, so arrows, x and y, using the velocity values. And so what that gives us is this map of how the glacier is flowing. We can then do the same thing. This is basically the same exact code, but do the same thing with a different velocity map, basically showing different models estimate different flow maps depending on how the models are configured. Finally, and we're pretty much at the end, we can compare those model estimates to thicknesses, measured thicknesses from satellite observations. So here we're creating a figure and an axis, and then attaching Python, attaching the data set to that figure and axis, setting the color map, creating the color bar, and what Salem has done for us is it's given us the background, the backdrop. It's given us the topography, because in SMAP, there's the topography also. In SMAP up above, we specified that we were reading in topography, des.topo.data. So we kind of built the groundwork, so we didn't have to keep adding that in. Okay. And this is doing the same thing, but for the different thicknesses. And finally, we are going to use OGGM, and let's go find where we defined tasks. I think we defined tasks from OGGM. So we have these different yeah, that's pretty opaque. Basically, OGGM has built in a bunch of different glaciology-specific calculations that it can perform. And so we do those calculations, and what comes out are things like mass balance above a specific altitude point, that, as I'm not a glaciologist, I won't pretend to hold forth on. But the point is to say that the tools that we have with Xarray, with Pint, with plotting libraries and projection libraries like Salem, allow you to go from raw data to scientific analysis or industry analysis pretty efficiently and quickly. And that's just absolutely cool. So that's where we end it. Any questions?
I have a question about coordinates and dimensions. What's the difference between them?
Yeah. So let's go find a data set to look at. So in pandas, you think of columns and rows. Like a spreadsheet, you think of, right, like columns along the top, going up and down, rows going side to side. And so if you want to know the location of a cell on a spreadsheet, you can know that x and y completely define the location of any point on the spreadsheet. They're orthogonal to each other. So in a similar way, if you add a third dimension, like in space, if you have x, y, and z in this room, we could specify where any point in the room is. Dimensions in an Xarray data set are that coordinate system. I shouldn't use the word coordinate system. Dimensions are that indexing system. So if you have 3-dimensional data or 5-dimensional data or whatever, you need 1 dimension per axis of data in order to uniquely define where each point is in your, if it's 3 dimensions, cube. However, it could also be the case that you want other ways of referring to the data that are in your cube that are not just x, y, z, but relate to x, y, z. So in that case, you would say, I want to create a coordinate that is a combination of x and y that will also relate to the data. So each data point is uniquely defined by x, y, z, but also has this coordinate which is like x, y, or something like that.
I think the sort of formalized way, because I'm still not 100%, but I think, so you brought in the z-axis. So now I want to imagine this. Like, imagine this room has infinity sensors in it, right? So we get a data set where each sensor has a position on one axis, on another axis, and on a third axis, because every sensor is a certain amount of inches from, or feet, meters, whatever, from the corner in one direction, from the corner in another direction, and at a certain height. So that's 3 dimensions. And then these right? And then the sensor, each sensor also measures temperature. So that's a 4th dimension.
Yes.
Right? So, and then the sensor measures over time. So time is a 4th dimension. Now, where I get hung up, so when you were doing that squeeze, that would be like, give me all of the and so let's say that the sensor is measuring temperature and humidity, okay? So when you were doing the squeeze, you would do something like, okay, give me the temperature and humidity of every single sensor at a specific point in time. So in that case, time turns into a coordinate from being a dimension.
Time was both a coordinate and a dimension.
Okay.
And when you said, I want only at a specific time, then we created a data set that had time, that had a dimension, time, and a coordinate, time, that was only 1. So you could squeeze it away because it wasn't necessary to describe the space.
Okay.
Here's maybe another way of thinking about coordinates versus...
But can I just to finish this? So what are temperature and humidity in this case?
Data variables.
Okay, yeah, because I was trying to imagine, I had a consultation where someone was asking me a question about YouTubers and like their views and subscribers over time. And when you were describing this, I was trying to think, oh, is this a 3-dimensional thing where it's time versus subscribers versus viewers? But it isn't, because both subscribers and viewer numbers are defined in terms of time. Like, subscribers and viewers may be correlated in some way, but they still are dependent on time.
So those are both data variables.
Those would both be data variables. Okay.
Because they don't require each other, they only require time.
Yes.
But, okay. Okay. So
Sorry for hijacking.
no,
your
this is good. So let's say what were the data variables?
Viewers, subscribers, and views.
Okay, subscribers and views. So our dimension is time, and time is in years. But maybe you also want to be able to describe in terms of decades. So then you could have a coordinate that is decades. The coordinate would relate to the dimension that is time. And so so your data set would have that coordinate decades, but the data variable subscribers or views wouldn't depend on decades. It would depend on only time.
So do you always have
Years.
So do you always have fewer dimensions than coordinates?
You always have you cannot have more dimensions than coordinates.
Okay.
Yes, you can have more coordinates than dimensions, but you must have at least as many dimensions as coordinates.
So coordinates is like a customized description of dimension.
Coordinates is like dimensions plus whatever else you want.
Okay.
So each dimension must also be a coordinate.
Oh, isn't it vice versa? Dimensions is like the basic
Yes.
things, and coordinates is like the different ways we call, like we describe, like we can describe the years like by decades or by centuries, things like that. So, okay. So isn't it like vice versa? We should have dimension first, and then coordinates should contain less information than dimensions, right?
I think we're saying the same thing.
Same thing. Okay.
You only a data set, if it has two dimensions, will have two coordinates, and those coordinates will be the dimensions.
Yeah.
You could also have other coordinates that relate to your two dimensions.
Okay.
Time and the height, I don't know, or whatever.
Well, in this case, in this case, what I was trying to explain to the student was that because they wanted to track viewer and subscriber numbers of different YouTubers over time.
Mm-hmm.
And I said that could all be collapsed into a two-dimensional data set, but where what is unique for each row is the combination of YouTuber plus time.
Two
Like
dimensions.
They were thinking about it in terms of that it was always the case that time would be, every row would be a unique time. So they wanted to stack YouTuber, and I was just like, well, you can do it that way, but that would be like a pivot table type thing, where you would have individual times and then subscriber views, YouTuber A, their views and subscribers, then YouTuber B, et cetera, et cetera. Whereas if you melted it back into a spreadsheet type shape, so to me a spreadsheet is inherently two-dimensional, but because the primary key is based on two variables, the time and the YouTuber, then that maybe is two coordinates. I don't know.
It's two data coordinates.
Okay.
It's because you would have, it's two spreadsheets. One spreadsheet is, both spreadsheets have as dimensions time and subscribers or whatever. YouTubers. Time and YouTubers.
The name of the YouTuber is like a categorical variable.
Exactly. Mm-hmm. And then one would be views, one spreadsheet would have the values that are views, and one spreadsheet would have the values that are whatever. And so, yeah, so in Xarray that would be a two-dimensional data set with two data variables.
So in the picture there, YouTuber name would be orange.
Yes.
Time would be dark orange. Subscribers would be pink.
Yes.
And viewers would be blue.
Exactly.
Okay.
Yes.
And then I'm still not entirely sure the relationship between coordinates and dimensionality, but
Yeah, it's like what I'm curious about is how can we uniquely find a cell? For example, you mentioned if we have x and y as dimensions, however, we can plus time or height, like things like that, in coordinates. But if a variable is like two variables at the same x and y, but at different heights, how do you find?
That sounds like a third dimension.
Three-dimensional.
That would be a
okay.
third dimension.
I see. Oh, I see.
Yep. If you need a third dimension to describe where the variable is, then that is going to be a dimension.
Oh, okay.
Yep.
I see.
You can get by with only ever thinking of dimensions and coordinates as the same thing until you can't. But like as a baseline, that's a good first understanding.
yeah, I think naming them coordinates is really tricky.
Cheers.
Yeah.
That's my take home. I'm gonna put in a pull request.
Yep.
Yeah, it sounds like a group buy thing.
Yeah. Like,
group buy 2000 and 2010, that's a decade. So.
Yep, totally. I think you can group by an Xarray.
Yeah. Thank you. That's my question.
Yeah, it's a great it's like the fundamental question of understanding Xarray.
Yeah.
Cool.
Thank you.
Yeah.
Yeah, thanks.
Thank you for sharing.
Semester, I really learned a lot of